All right, hi everybody. So this is a video with an example calculation for how to find the mole ratio in a hydrate. Okay, so first of all, what is a hydrate? A hydrate is a ionic compound that contains water inside the crystal structure. It's important to note the water is not trapped there, but the water is actually bound to the ions in the ionic crystal structure, and there's a very specific number of waters that will form in the compound as it crystallizes. So the goal of this is to figure out how many waters are in the crystal structure per formula unit. Okay, so that should be a fairly defined ratio. Okay, so I have two pictures here because we're using cobalt chloride hydrate as our example here. So most hydrates, or many, maybe not most, but many have a vibrant color that looks like it could be pink. The one you'll use in lab will be kind of a bright blue. Okay, so they might have vibrant colors, and then once you drive the water off, you make it anhydrous, meaning no water. You'll frequently have a much more mellow color or even no color at all once the water has been driven off. The water really kind of helps bring the color out in those crystals, and for reasons that we won't really get into unless you go much further in chemistry, in organic chemistry. All right, anyway, so let's look at how to do these calculations. Here is a example set of data. Notice we have some tray. You might have a crucible if you're doing it the virtual lab. You'll have some tray or crucible. Then you put some powder in there, and then as you heat it, the water will start to evaporate and boil out of the crystal structure. As the water leaves, go figure, your mass goes down. Okay, so it continues to go down. Notice we heat it up the first time and we lose some mass, so some water leaves. But then if we heat it up again, we lose even more. And then we heat it up again, we lose even more until the mass eventually levels off. So the mass is gonna drop, and then level off. We want the mass once it's leveled off, because that means that all of the water has boiled out of the crystal structure. Okay, so these two masses here after the first and second heating are really fairly meaningless because those numbers contain some amount of water that we don't know how much. So importantly, we need the initial mass, and we need the mass once it's leveled off, because that's when all the water has been driven off the powder. Okay. So here's how we calculate that then. So the first thing we have to do is figure out the mass of powder that we had. So we take our total mass initial minus the tray, and this gives us the mass of the hydrated ionic compound. Okay, so this is the mass of the powder with the water still in the crystal structure. Then we take our final mass once it's leveled off minus the tray, and this gives us the anhydrous powder. Okay, what we can do is we take these two numbers and we subtract them, and we get the mass of just the water that was in the crystal that we boiled off. Okay, in order to figure out the ratio between the water and the formula units of the crystal or ionic compound, we need to find the moles. So we take our mass of water that we just found, that 1.280 grams of water, times a conversion factor where we divide by the molar mass of water, in this case 18.015 grams of water for every 1 mole of water, and we get 0.07105 moles of water that came out of the powder. Okay, we're then going to do the same thing with the anhydrous powder. So we don't know how much water is in this guy, so we're not really going to use that mass, but we do know that this is anhydrous, meaning all the water is gone. Okay, so since we were using cobalt chloride, we took our mass of cobalt chloride, again multiplied by a conversion factor where we divide by the molar mass of cobalt chloride, 129.839 grams of cobalt chloride for every 1 mole. And we get this many moles of cobalt chloride that were in the anhydrous powder. Okay, we can then take those two mole numbers and divide them. So we take our moles of water, this 0.07105, divided by the 0.01184 moles of cobalt chloride, and we get a ratio of 6. What that means is there are 6 waters for every 1 formula unit of cobalt chloride, and they're bound in that crystal structure. So then our formula becomes CoCl2, 6 waters, cobalt-2 chloride hexahydrate. Okay, importantly, my ratio came out very nice and neatly because I made up the numbers that we used in the lab. We will frequently not